Today we begin our lecture with the advantages of involute profile. Because of these advantages, we find involute profiles are most commonly used in mass produced gears. So, advantages of involute gear tooth profile. In our last lecture, we have already seen that a pair of involute profiles can maintain the conjugate action, that is, it satisfies the fundamental law of gearing, that is, it maintains constant angular velocity ratio between the two shafts. So, first and foremost is maintains conjugate action. However, as I said earlier, this is not so much of importance, because if one is given any smooth curve as one profile, one can find another profile which will be conjugate to the given profile. So, this is not the unique choice of involute profile which maintains conjugate action. There are other advantages of involute profile over and above that it maintains the most fundamental requirement, that is maintaining conjugate action. The second advantage is that operating pressure angle is constant. If you remember, in our last lecture, we denoted this operating pressure angle by the symbol phi, which is the angle between the line of action and the common tangent to the pitch circles. Maintains constant pressure angle. Operating pressure angle is constant. We will get back to the same figure which we discussed last time to show what is the advantage if the pressure angle remains constant. What is the consequence of this pressure angle remaining constant? And the third advantage is that a pair of involute gears maintains conjugate action even if the center distance between the gears are changed. That means we have a pair of gears, we can mount them with a little different center distance, even then this conjugate action will be maintained. Even if center distance between the two gears, that is between a pair of center distance between the pair of gears changes. These 2 points, as I said, I will explain with reference to the figure that we discussed last time. And the last but not the least, the most important reason why involute profiles are so common is that ease of production. Why it is easy to produce involute gears? Because gears are produced, gear teeth are produced by a process called generation. That is, again we use the conjugate action, but not between a pair of gears, but between a rack and a pinion. And it is the conjugate rack of an involute profile is a straight tooth rack. If we have an involute profile, we will see this later, that the conjugate rack tooth if this is a rack whose tooth profile is straight, then it can maintain conjugate action with a involute gear. And it is such a straight sided rack cutter is used to produce the involute tooth profile on a circular gear blank. This is I can say it is an involute rack, which is used as the cutter, and on the cutter it is much easier to produce state size than any complicated curve, and it is this involute rack cutter which can maintain conjugate action with an involute tooth profile of a gear. So this is called involute rack cutter. Why the involute of a rack is a straight line, this point again will be cleared in today's lecture a little later, that the involute of a straight line is another straight line. Like we have seen, involute of a circle is a curve. So if this radius of the base circle goes to infinity when the gear gets converted into a rack, then this also becomes a straight line. All these points we will make clear in today's lecture. So let me get back to that figure where I showed the pressure angle, and now we will show what is the advantage of this pressure angle remaining constant in a pair of involute gear teeth profile. Let us get back to this figure which we discussed in our last class. These are the two base circles of radius RB1 and RB2. These are the pitch circles of radius RP1 and RP2, and it is the common tangent to that base circle which we call line of action, and this line of action AB makes an angle phi with this common tangent to the pitch circles. This TT is the common tangent to these pitch circles of radius RP1 and RP2, and this angle phi what we call operating pressure angle. Now as we have already noted, because the line of action just remains AB, this pressure angle does not change as if the profiles are involute. The pressure angles remain constant during the entire interval. Now what is the advantage that the pressure angle remains constant? If we neglect the friction force between the gear teeth, which if it is well oiled and well lubricated, friction force is not very large, the driving effort is along the common normal. If this gear is driving this gear, then most of the force is acting through this along this common normal. So if this normal force we call say N, then the torque that is transmitted is N times the base circle radius, because this line of action N is along AB and this angle is 90 degree. So the torque acting on this gear 2 is N into RB2, and if this torque is torque that is transmitted to gear 2. Now if this torque remains constant, then N remains constant, because RB2 is constant, the base circle radius. If N remains constant, then you see both the magnitude and direction of this force N is remaining constant, which means the bearing reactions here and here, because there is the same N which is acting on this gear also. So the direction and magnitude of N both remains constant because phi does not change, and if torque is steady torque, if we are transmitting a constant torque, then this torque is also constant, which means magnitude of N is constant. Because phi is constant means the direction of N is constant, which means the bearing reactions while the gears are transmitting a steady torque remains the same, which means the bearings are not subjected to any dynamic reaction. The magnitude and direction both of the reactions remain same so long a steady torque is being transmitted. This enhances the life of the bearings which are used to mount these two shafts on the foundation. Thus the pressure angle remaining constant implies that under steady torque the bearing reactions are not dynamic, they are static torque. That is the advantage of pressure angle remaining constant. The third advantage we discussed was that suppose this pair of gears, right now the center distance is O1, O2. Suppose this gear remains where it is, only this gear is shifted a little bit upward. then what we will see that it is the same involute profiles will be useful to maintain the conjugate action. Let us see what is the center distance. Center distance O1, O2 is Rp1, the pitch circle radius of the first gear, plus Rp2, pitch circle radius of the second gear. And we have already noted that base circle radius Rb is nothing but Rp cosine of phi, where phi is the operating pressure angle. So we know Rp1 by Rp2 is same as Rb1 by Rb2, because Rb1 is Rp1 cos phi, Rb2 is Rp2 cos phi. Cos phi cancels, so this ratio remains same. So what we see that so long the gears are same, that is the base circle radius remains same, Rp1 by Rp2 remains same. With the center distance changing, it is Rp1 plus Rp2, this quantity is varying, which means with varying center distance, if the center distance varies, the pitch circle radius Rp1 and Rp2 both change. Rp1 and Rp2 both change, but the ratio of Rp1 and Rp2 that remains same. So it is the same angular velocity ratio omega 1 to omega 2 is maintained. Only thing what changes, because Rp1 and Rp2 is changing means phi is changing, because Rb1 is not changing, and Rb1 is Rp1 cosine phi, where phi is the pressure angle. Rb1 is not changing because the gears are not changing, but with changing center distance Rp1 is changing, which means phi is changing, because this common tangent, if this circle is shifted a little bit upward, the common tangent between these base circles will change. That means this angle phi will change. So pressure angle changes a little bit, but the same angular velocity, constant angular velocity ratio is maintained by the pair of gears even when the center distance changes a little bit. That was the third advantage. And the fourth advantage, as I said, will be explained later when we will be able to show that the involute of a straight line is a straight line. That is, for a rack, to maintain conjugate action with an involute profile, the tooth profile on the rack will be straight like trapezium, as we have shown earlier on the board. Because involute profiles have all these advantages, as I said earlier, they are almost universally used in mass produced gears. And as a consequence of this mass production of involute gears, they have been standardized. There are various standards, but I can mention some typical standards which are more commonly used, like British standard for involute profiles. So involute tooth profile, some standard dimensions are the most common value of the pressure angle, operating pressure angle, phi is 20 degrees. Some old gears which were cast, it also had a value phi equal to 14.5 degrees, but these days most gears, involute gears, will have an operating pressure angle equal to 20 degrees. Similarly, the value of the addendum, which we defined earlier, A, is equal to the module, where M is module. The gear teeth is described in terms of the module of the gear teeth, and the standard value of the addendum is equal to module. Similarly, dedendum which we denoted by B and which is always more than A, the most common value is 1.25 times the module. M is the module which is expressed in millimeter for metric ds, and A is equal to the module M and B is equal to 1.25 M. These three standard values we may take if unless otherwise specified. As I said, involutes are most commonly used, and geometry of involute teeth is a very vast subject. We are not going to get into all the details of involute teeth geometry, but I will give you a little glimpse or a little basic idea of this curve involute, which we call involutometry. And the results that we will obtain from this involutometry will be very useful to determine various proportion of the gear teeth which are involutes. So, we can say application of involutometry in gear tooth geometry. I repeat, we will discuss of course only the very basics of this gear tooth geometry. You can always refer to handbooks for the details that you may like to know. So, let me first say what is involutometry. Suppose this is the base circle with the center here, and we start unwinding the string from this base circle from this point A, and by unwinding the string I generate this involute. So, at this is the string length which is same as this arc length, because this string was wound onto this cylinder and now it has wound up to this point, and this is the involute from this base circle. So, the string is tangent to the base circle. So, this radius RB, base circle radius, this is perpendicular to the string. Now, at this point the involute takes off radially. So, this radius is tangent to the involute at this instant, and at this configuration this is the string which is perpendicular to the involute. So, the tangent is perpendicular to the string, this is tangent, this is the tangent at this point, say B. This radial line is tangent to the involute at A, and this line which is perpendicular to the string at the point B is the tangent at the point B. And this angle between these two tangents I call the roll angle theta. Theta is called roll angle. This line does not look like perpendicular, so let me draw it correctly. This is O. So, this line is perpendicular to the string, this radius is also perpendicular to this string which is tangential. So, this is parallel to this. So, if this angle is theta, this is also theta, the roll angle. That is, the string has unwound up to this point B, where the roll angle is theta. This particular point on this involute, this is the involute, this distance OB is the radius vector, let me call it R. If this circle, this represents the base circle of a gear and the gear is rotating about the point O, then this particular point has a velocity which is perpendicular to OB. This is the direction of the velocity and this is the normal to the involute. So, that is the line of action. So, at this point, this angle between the normal and the direction of the velocity, normal really indicates the direction of the force at this particular point. This angle is called psi, which we will call involute pressure angle. This is the angle between the line which is perpendicular to OB and the string at this configuration when you have reached up to the point B. Please note that this is not the operating pressure angle which we discussed in case of a pair of gears. This is only one gear we are talking of, one involute we are talking of, and this particular angle between the direction of the velocity and the direction of the normal to the involute, I call it involute pressure angle. Now, this line is perpendicular to the tangent and this line is perpendicular to the direction of velocity. So, this angle is also psi, involute pressure angle. Theta is the roll angle, psi is the involute pressure angle. Theta is the angle between these two tangents at A and B, which is same as these two radius at A and corresponding to B, and psi is the involute pressure angle. So, let us say base circle radius is RB. And this is the string length is the radius of curvature of the involute at this point B. If this is the involute, at every instant the radius of curvature is nothing but the string length which has been unwound from the base circle. So, rho is, if I call this point C, then BC is the radius of curvature rho. So, what we see, rho is given as square root of R squared minus RB squared. Where R is this radius vector of the point B measured from the center of the base circle. And if I use this angle as a polar angle to define the involute curve, what is this angle? That is theta minus psi. This angle is theta minus psi. And we also see this rho is same as this arc length AC, because this is the length of the string and this was the original length of the string. So, AC is nothing but rho, which is same as RB into theta. And also you can see tan psi is rho by RB. If this angle is 90 degree, this is rho, this is RB and this is psi. So, tan psi is rho by RB. So, we can write tan psi is rho by RB. And from here we see rho by RB is nothing but theta. So, I can write theta minus psi as tan psi minus psi. Theta is rho by RB and rho by RB is tan psi. So, this angle that the line OB makes with this original radius OA, that angle is tan psi minus psi. And this is given a name which is called involute function of psi. And we can also see RB is nothing but R of cosine psi. So, we can write base circle radius is related to R as R cosine psi. So, everything has been found in terms of this involute pressure angle psi, which keeps on changing at various points. The distance from O I can get as RB by cos psi, and this angle I can get as tan psi minus sin psi, which is called involute psi. It is very easy to see that if one gives me the value of psi, I can calculate involute psi very simply. This is called involute function, just like sin, cos, we call it involute of psi. Given the value of psi, it is easy to calculate involute of psi, but not the other way around. So, for this tables are available, just like tables of sine, cosine, tan, log. I can get the value of psi if you give me the value of involute of psi by consulting that table. Now, at this stage, I will be able to show that what happens to this radius of curvature of the involute profile as RB increases. As I said, when RB goes to infinity, the gear gets converted into a rack. So, under that situation, what is the radius of curvature of the corresponding involute profile? So, let me now say what is the radius of curvature of the involute tooth profile of a rack. Rack means where RB goes to infinity. We have already got rho equal to square root of r squared minus RB squared, where r is the instantaneous value of this distance. So, if we start from A and go up to some point by changing initial value of r is RB, and then I go to RB plus delta r. Let us say as I start from A, I go a little away from this when r changes from RB to RB plus say some delta r. If I substitute it there, what we get? We get twice RB into delta r plus delta r squared to the power half. This is the value of rho as we go out from this point A. Now, if RB goes to infinity, it is obvious that rho also goes to infinity, and if the radius of curvature goes to infinity, which means this profile has become a straight line. That is what we said, that if we have an involute rack, then the tooth profile from the base circle as it comes out in the form of a straight line. So, the tooth profile of an involute rack is a straight line, and which can maintain conjugate action with an involute gear or involute pinion, and that gives the advantage that I can use such a rack cutter to generate the involute tooth profile on a circular gear blank. Let me now repeat what we have just now discussed with reference to this figure. This is the base circle, this is the center of the base circle, and involute is being generated starting from this point A. When the involute, if I consider a point I here, then the string at this configuration corresponds to this line IB, which is tangent to the base circle. OB is the radius of the base circle, which we denoted by RB. The instantaneous polar radius of this point I denote by R. The tangent at A to the involute is this radial line, and the tangent at I is this line. The angle between this tangent at I and the tangent at A, this angle theta, we call the roll angle. Theta was defined as the roll angle. If this I take as a gear and the gear is rotating about the point O, then the velocity of this point I is perpendicular to OI. Say this is the direction of the velocity of the point I if it happens to be a point on the gear. And the string which is normal to this gear tooth profile or the involute profile, that is the normal to the involute at the point I. And the angle between this velocity direction and this normal, which is nothing but BI, I call psi. This is normal and this is a tangent, so this angle is 90 degree. This is also perpendicular to this string BI, which is tangent to the base circle. So this line, the tangent at I, and this radius OB are parallel. So if this angle is psi, then this angle is also psi. Similarly, if this angle is theta, this angle is also theta, because this line is parallel to this line. So theta is the roll angle and psi is this angle. Now the polar angle of this line OI from this vertical line, that is the radius through A initial point, this angle, which is theta minus psi, we defined as involute of psi. Involute of psi is this angle, which is theta minus psi. And what we have seen, that this length AB is nothing but RB into theta, and the string length BI is also equal to AB. So this rho, which is the radius of curvature of the involute profile at I, the string length is the radius of curvature, rho, this rho is nothing but RB into theta. From this triangle OBI, I can write tan of psi, because this angle is 90 degree, tan of psi is also rho by RB. So we can write rho is RB tan psi, which means theta is equal to tan psi. So this involute psi, which is theta minus psi, I can write is as tan psi minus psi. Then we also found that expression of rho in terms of R and RB, which we wrote as rho equal to square root of R squared minus RB squared. As we draw this involute from starting from this base circle, the R changes from RB, it increases from RB, say by a value delta R. Then substituting in there, cancelling RB, what we found, that expression of rho turned out to be twice RB into delta R plus delta R whole squared. So this clearly shows if RB tends to infinity, then rho also tends to infinity. That means right from the point A, as soon as R changes from RB to plus small delta R, the radius of curvature becomes infinity. That is the involute of a straight line. When RB goes to infinity, this base circle becomes a straight line. That is the gear is converted to a rack, and the involute profile becomes a straight line, because radius of curvature is infinity, which tells us a rack, involute rack tooth profile looks like a straight line. Just now we have discussed the basic geometrical relationship between an involute profile and its base circle. These relations are very useful for studying gear tooth geometry, as I said earlier, and here we discuss an example. Suppose this is an involute tooth profile which has been generated from this base circle. Suppose the thickness of the tooth, as we see, keeps on varying from the base circle up to the addendum circle. Suppose the thickness of the tooth at any point x, which is defined by the polar radius Rx. This point x is defined by this distance OX, and the thickness at this level I denote by Tx. Then when this polar distance changes from Rx to say Ry, I get to this point y, and I want to find what is the thickness of the tooth at this level, that is Ty. So Tx is given, I would like to find Ty, and Rx and Ry are given. To do this, first we note when the involute was at x, the string is dx. This is the length AD, which has become dx. And when we come to the point y, the string is represented by by. This is the tangent. By is same as the arc length AB. So, the angle between this OX and OD we defined as the psi. So, I write it as psi x. Corresponding to x, d is the xd is tangent to the base circle, and the angle between OD and OX I call the involute pressure angle at x, which is psi x. Similarly, the involute pressure angle at y is the angle between OY and the tangent to the base circle from y, which is YB, that is what I call psi y. We have already seen the base circle radius RB. This is also base circle radius RB, and this can be written as RB is nothing but Rx cosine psi x. It is also equal to Ry cosine psi y. So, if you are given the values of Rx and Ry, I can get psi x and psi y. Now, how Tx and Ty are related? For that, let me consider this angle AOC. OC is the mid line or the symmetric line of this gear tooth, OC, and the angle that OC makes with OA I call this angle. So, angle AOC I can write as Tx by 2 divided by Rx, that I am getting this angle. This angle is Tx by 2 divided by Rx, and this angle is nothing but involute of psi x. At the point x, the angle that OX makes with this starting line OA I defined as involute function of psi x. So, angle AOC is nothing but Tx by 2 divided by OX, which is Rx, plus involute function of psi x. And if you remember, involute function is tan psi x minus psi x. Involute of psi x is tan psi x minus psi x. And AOC, the same angle, I can also write as this angle, which is Ty by 2 divided by Ry. So, Ty divided by 2 Ry plus this angle. This angle, that is the angle between OA and OY, which is nothing but involute of psi y. This angle is involute of psi y. So, this plus involute of psi y. So, if Rx and Ry are given, I can find psi x and psi y from this relation. Once psi x and psi y are known, I can find involute of psi x and involute of psi y, because involute function is tan minus the angle. Involute function of any angle psi x is tan of psi x minus psi x. Of course, psi x must be measured in radian. So, from this relationship, if Tx is given, Rx is given, Ry is given, I can find Ty, which is the only unknown, because psi x and psi y I have already found out from here, and in using the involute function I can find involute of psi x and involute of psi y. So, thus for the gear tooth geometry, as we see, if you give me the thickness at any level, I can find the thickness at any other level of the same involute tooth profile. For continuous transmission of rotation from one gear to another, it is obvious that it is imperative that a pair of teeth must remain in engagement before, at least until the next pair of teeth comes into engagement. It should not happen that one pair of teeth has lost his engagement and the next pair of teeth has not come in engagement, because then there will be no transmission. So, to maintain continuous transmission of rotation from one gear to another, it is imperative that a pair of teeth must continue to be engaged, must continue to remain engaged at least until the next pair of teeth has come into engagement. This phenomena is studied in terms of a geometrical quantity which we call contact ratio. Let me now define the contact ratio and try to get the expression of this contact ratio. So, we study contact ratio for involute tooth profile. We use the symbol MC indicate the contact ratio. Let us say this is one base circle and the center of this gear is at O1, and the center of the other gear is at O2. This is the other base circle. Base circle 2, this is base circle. If you remember that it is the common tangent to this pair of base circles if I draw the common tangent to this pair of base circles, that defines the line of action. This is A and this other point of tangency is B. So, we know the contact between a pair of gear teeth will always lie on this line AB. Now, let us talk of one tooth of this gear. Suppose this gear is rotating this way, and through the teeth action by teeth engagement it is rotating this gear in this direction. So, if we consider a tooth on this gear, the first it comes into engagement at its outer circle or the addendum circle, and because the contact point must lie on this line, when the addendum circle comes here in contact with this line AB, that is where the contact starts on this face of the gear tooth. This is one gear tooth. Now, how long now this gear starts rotating this way? How long this tooth will remain in contact with the tooth on the other gear, gear number 1? So long the outer circle of this gear is in contact. So, this is the addendum circle of the gear 1. Let me call it radius RO1, that is the outer radius of gear 1, and this is RB1. So, the contact will, as this tooth rotates, this tooth comes here, and when it tooth on this gear which is pushing it. Let us say here, if I draw this gear, this tooth comes and rotates, and when this outer circle leaves this line, the contact is lost with this particular gear. So, if I draw this tooth here, this is where the contact